Good morning and welcome to today's lecture on Chapter 5.6, Applications and Models for Growth and Decay and Compound Interest. Today we're going to solve applied problems involving exponential growth and decay, and we're going to solve applied problems involving compound interest. Population growth. The function p of t equals p sub 0 e raised to the power of kt, where k is greater than 0, is a model many kinds of population growth. This works for finances, it works for science, it works in nature, etc. And in this function, p sub 0 is the population at time 0. Now I want you to be aware that when we're talking about population growth, we're talking about the population of anything. If we're talking about money, then your population is how much money you have. So the population at time 0 for an investment would be the amount you put in initially. Okay, p of t, the function, is the population you have after a specific amount of time, t. And then k is the exponential growth rate. And the growth rate unit must be the same as the time unit. So if you're doing a growth rate, an annual growth rate, then your t is going to be in years. In some cases, you might do a growth rate in days. For example, I know that for rabbits, I think the double time of a population of 100 rabbits is 13.6 days. So your growth rate would be a daily growth rate, or yeah. If you look at a population growth graph, we can see that what we have here is a graph that is growing, and it's getting steeper and steeper over time, which is why we say, things are growing exponentially, meaning that they're growing very fast, etc. And we can see that we have an exponential growth rate. We have an exponent here. Okay, so let's look at an example. In 2009, the population of Mexico was about 111.2 million, and the exponential growth rate was 1.13% per year. Find the exponential growth rate, estimate the population in 2014, and after how long will the population be double what it was in 2009? Well, at t equals 0, the population was 111.2 million. And so we substitute 111.2 for p sub 0, and 1.13% is equal to k, or really it should be the decimal version, which is 0.0113, to obtain the exponential growth function. Here all we've done is we've plugged in two values, p sub 0, which is our initial population, 111.2, and also our growth rate, which is 0.113. It's the percentage rate put into a decimal form. So it's very simple to estimate the population in 2014. This would be 5 years after 2009, which is our initial point. So we're going to have p of 5, because 5 years is t equals 5 because this is 5 years since 2009. And our growth rate is an annual growth rate per year, so our time is per year as well. So we simply plug in 5 into our growth function, and we get approximately 117.7. Don't just watch this. I would suggest that you actually try to put this in your calculator and make sure you get the proper answer. This little squiggly is just means approximately equal to. C, after how long will the population be double what it was in 2009? Well, in 2009, the population was 111.2, so we're trying to figure out when the population will be 222.4, right? So we plug this in and set it up and try to solve for t. So we get 222.4 equals 111.2 e to the 0.0113t. Okay, so we're trying to solve for t. This is just what we've learned to do in the in an earlier section. We need to get the exponent out, bring it down by taking the log of both sides. But before we do that, we're going to divide both sides by 111.2 just to make this simpler. So we get 2 equals e to the 0.0113t. We now take the natural log of both sides. And notice on the right side of the equation, since we're taking the natural log of e to an exponent and the base of natural log is e, these just cancel out and I get 0.0113t on the right side of the equation. Here I'm going to divide both sides by 0.0113 and then just put it into my calculator and calculate it, and I get t is approximately 61.3 years. So the population of Mexico will be double in about 61.3 years after 2009. Okay. The function p of t equals p sub 0 e to the kt, which is what we just saw before, it can also be used to calculate interest that is compounded continuously. P sub 0 is the amount of money invested initially. P of t is the balance in your account after t years. T is the number of years, and K is the interest rate compounded continuously. Suppose that $2,000 is invested at interest rate K, compounded continuously, and grows to $2,504.65 after 5 years. What is the interest rate? Find the exponential growth function. What will the balance be after 10 years? And how long will the 2,000 have doubled? How long will it take for the $2,000 to have doubled? Well, we know the exponential growth function is just p sub 0 e to the kt, and since we started with 2,000, that's our p sub 0. And we know that p of 5 is equal to $2,504.65. So we can put this into our formula. We get 2504.65 equals 2,000 e to the 5k, because this is what our investment grows to in 5 years. Again, we have an exponential equation that we need to solve, so divide both sides by the 2,000. Take the natural log of both sides. Again, the right side of the equation, the e and the log will cancel out since we're taking the natural log of a base e exponential. This is just going to become 5k on the right. And then dividing by 5, we find our k, which is approximately 0.045, which is actually 4.5%. Okay. So to find the exponential growth function, we just plug in p sub 0 and the k, or the growth rate that we just found, into the kind of generic formula. And so we get p of t equals 2,000 e to the 0.045t. This is just plugging in the value we found in part A and the initial investment that is given in the problem. So to find the balance after 10 years, all we have to do is plug in 10 for t. We want to know what's going on 10 years later. Put it in our calculator, and we get $3,136.62 approximately. And then the last thing we want to do is to find out how long will it take for the $2,000 to be doubled. Okay, so we can plug in 4,000 equals our formula. Divide by 2,000. Take the natural log of both sides. The right side will simplify, divide by 0.045, put it in our calculator, and we get 15.4. Thus, the original investment of $2,000 will double in about 15.4 years, which is actually not a bad interest rate. It's a pretty good one, actually. One of the things that's interesting is that doubling time actually doesn't really depend upon the initial population. We can see here from the formulas how they're related, that the double time, which is indicated by capital T, is simply equal to the natural log of 2 divided by the interest rate or the growth rate. Okay, so it's very easy to find the doubling time if you know the interest rate, or to find the interest rate if you know the doubling time. The population of Kenya is now doubling every 25.8 years. What is the exponential growth rate? So here we have our natural log of 2 over k. The interest rate of the growth rate equals the natural log of 2 over the double time. We've got the double time, so we just plug that in. We put it in our calculator and we get 0.0269, which is approximately 2.69%. Okay. The growth rate of the population of Kenya is about 2.69% per year. So these are pretty straightforward if you know the basic formula. All right. Exponential decay. Exponential decay works the same way as exponential growth, except instead of whatever our population is increasing for growth, it's decreasing for decay. And so the only thing that's different about this formula is that there is a negative in the exponent. So the exponent is technically negative, even though we still say our growth rate or decay rate should be a positive value. Okay. Again, our p sub 0 is our initial population. Our p sub t is the amount of whatever left at time t. T is our time, and k is the decay rate. The half-life is the amount of time it takes for the substance to decay to half of the original amount. This is how they do carbon dating of fossils. Carbon decays at a specific rate, so if they figure out how much is left, a percentage, then they can figure out how old something is. So on the left you see a growth rate chart, and on the right you see a decay growth rate graph. And you can see that they're pretty much mirror images of each other. One is growing fast and one is shrinking fast. Interestingly enough, again, the decay rate and the half-life t are the same pretty much as the growth rate and double time. So notice that we can figure out the half time when something is shrinking instead of growing using the same formula for as we did for double time, which is simply the natural log of 2 over the interest rate. And again, if we swap out k and t, we can find the interest rate given t, or we can find t given the interest rate rather simply. The radioactive element carbon-14 has a half-life of 5,750 years. The percentage of carbon-14 present in the remains of organic matter can be used to determine the age of that organic matter. Archaeologists discovered that the linen wrapping from one of the Dead Sea Scrolls had lost 22.3% of its carbon-14 at the time it was found. How old was the linen wrapping? Now remember, this decay in this example is about the percentage of carbon left in a fossil. So the first thing we need to do is to find the interest rate when the half-life t is 5,750 years. Well, again, this is really simple. K equals ln over t. Just, again, we can swap out k and t in the formula that you see at the top of the screen here. You can put k here and t here. Multiply both sides by k, divide both sides by t, and you get the same thing. So we plug this into our calculator and we get approximately 0.00012, which is an interest rate of 0.012%. Okay, but really what we need this for is to plug into our formula. So we get P of t equals P sub 0 e to the negative 0.00012 t. All right. Well, we know that that 22.3, it lost 22.3. So what's left is 77.7 of the original amount. Okay. So this is kind of a little bit tricky. A lot of students might have put in the 22.3 as the K. That's not true. They might have tried to use it someplace else. They might have put it over here. But notice what we need to do is to say that our right side of the equation, we don't know what the initial population was, but what we have left is 77% of that. So we can rewrite the equation as 77.7% times P sub 0 equals P sub 0 e to the negative 0.00012 t. Now immediately the P sub 0's cancel out, and we get an exponential equation. We take the natural log of both sides. The right side of the equation simplifies. We divide by negative 0.00012. and we plug it into our calculator, and we get T equals approximately 2,103 years. So the linen wrapping on the Dead Sea Scrolls was about 2,103 years old when it was found. So hopefully that this helps you manage and master these materials. Please reach out if you need any help.